And we're live. Welcome, everybody, to this week's Azure and AI Show. And Happy New Year. This is our first show of 2026. And with me this evening, we have two new speakers. We've got Palav and we've got Ishan. And with us here today, we've got Dan Ray as well. And we're due to have another speaker there to join us later. So we'll just kick off there. So with Palab, I'll just stick your slides up on the screen and over to you. There we can see it.
Yes. Thank you. Can I make it maximum in my screen?
Yeah, we can see your screen there now. Perfect.
Okay. So before I start, uh, uh, let me let me, let me start with the first one. Uh, my name is Pallav Haldar, and I am uh, almost 20 years experience in IT industry. So I'm currently affiliated with Cognizant Technology Solutions, and my field of expertise is enterprise application architecture along with supply chain optimization with AI and ML. So today I'm going to discuss and have some presentation about the predictive supply chain implementation in a AI Azure interface, so architecture, so that we can avoid the traditional delay and traditional blockage and barriers to overcome and optimize the total process to avoid the delay. So this is all the theme of my uh, presentation. So I am going one by one. So in the first slide is the technical slide. I'm going to the second slide, which is the motivation, introduction and motivation. Here, I clearly mentioned that what are the barrier and complexity of a supply chain process and how we are planning to overcome using Azure cloud native platform to overcome and build a AI-enabled system to avoid all the barriers along across the different international, continental, and domain region. There might be different kind of barrier, different kind of stacking environment, different kind of document approval, resilience. So there are few points which I have mentioned in that particular uh, slide. If you can see, global complexity is one of the major barrier, limited agility, AI advantage, Azure foundation. So main object is that today's supply chain is very complex, okay, and they are connected with one another and interconnected network of subdomain. So there might be, we don't have real kind, we don't have, suppose we are using in another continent, we don't have too much visibility to another subdomain, sub-process supply chain to make it work as soon as possible and to get all the required required material and every aspect of that from that subdomain supply chain. So there is always have some fundamentally lack of agility and real-time visibility required to navigate modern disruption. So in our my approach is in our modern era, we want to design and we have to design an artificial intelligence transformation paradigm using some integrated analytics service and some Azure using cloud native platform provides some foundation capability. So using those capability, we will build a optimized supply chain management process system which have some AI capabilities at enterprise scale level. So that way, all of you know that currently all the supply chain processes have some batch processing system. So if you run a batch, then it will finish the batch, the data will populate to the next system for the next system. So that way, lots of delay and agility, delay and also disruption came. So what we can avoid using modern era AI capabilities, machine learning approach, and it will integrate with the Azure cloud system. Native platform provides lots of predefined model and predefined foundational capabilities that we will use it and we will make the supply chain management system system more accurate and more uh, real-time visible, which is the main aspect and main requirement for each and any application, not only supply chain. So that we will do. So now I am going to the next slide. Next slide is key challenges in the supply chain, in the modern supply chain. If you see, there are multiple, there are thousands of challenges, but among which I feel that is need to be addressed to make it more interactive and more real-time scenario that I have shorted down and that I have put it in the slide. If you can see, data fragmentation. This is one of the major criteria that need to be addressed properly in each and every system before design. So here we are using Azure AI platform and his base capability model. So using that, we will try to mitigate this fast data fragmentation, which is the critical supply chain data remains in different system kind of, it's kind of ERP, warehouse, transportation management, TMS, and CRM, other systems, which we need to be integrated and fragmented properly before we move to the next step. It's kind of a data preparation, if you say in terms of artificial artificial intelligence or ML. So this kind of fragmentation we need to do. So we will use this platform for that. Then the second one is the data quality crisis, which is different kind of system has different kind of normalization. It's kind of a inconsistency of data. So if you, harmonization, we need to do the harmonization, and to do the harmonization, data quality crisis is one of the major criteria and blockage for every system. So that is one of the major fallback while you designing a supply chain management system using your preferred. Here we are doing using AI and Azure, so Azure framework. So, but this is the one of the what I can say. This is the one of the major barrier and major of the challenges in any kind of supply chain. It might be healthcare, it might be aerospace, it might be Medicare, different kind of way. But this. Similarly, there is other key challenges also like decision latency, reactive posture, and compliance pressure. So all the things that need to be addressed properly in terms of we doing some optimization using some model which are available in the AI as a platform, as a base platform. So then we will overcome this kind of a data fragmentation and data preparation stage where we will need to do all this, implement and address all these challenges and all these barriers which I mentioned in this slide. Then we can go ahead and able to design a proper application or app or system where we can have the real time update, real time scenario and real time posture of the supply chain management system which we are planning to build. So now I am moving to the slide number 4. Evaluation of the supply chain is kind of a history where you can see the different kind of uh, steps and process are there: deterministic logic, autonomous, then disruptive analysis, then predictive and perspective, and then autonomous intelligence. These are the four kind of processes that all the industry and all the experts are used to evaluate and design the proper real-time process for the supply chain based on the artificial intelligence and ML. Anywhere, if you use only artificial AI, not ML, these are the basic four architecture they can use process. Next, I'm moving to the next slide, which is the evolution. Next slide, which is the architecture of the Azure Theta architecture, which we will use for build a real-time supply chain, optimized supply chain application model. So if you see that particular slide, you can see that there are different kind of layer available in the Azure interface, so which we can use for our application building. So first one is the foundation and data layer. Second one is the intelligence layer. Third one is the orchestration layer. So this foundation layer is basically deals with the data, with the robust governance and quality control like data cleansing, data like some address cleansing, different kind of cleansing, different kind of normalization, some different kind of harmonization kind of thing. Then the intelligence layer, what it do, it's scalable. It's different kind of ML and AI operation, like it kind of based on the data, it calibrate the data, and on top of that, it will use to automate the training pipeline, distribution completing by creating some model and a kind of thing, applying some algorithm machine like linear regression kind of. For an example, I am giving you that kind of small thing. Machine algorithm they used to apply on top of the data and used to train the model. Orchestration layer. The next layer is the deployment layer, like CI/CD automation, real-time interface monitoring, continuous model improvements process. So CI/CD automation is related to the deployment process, which you can deploy the automation, your application deploy automatically using CI/CD integration. This kind of thing architecture leverages Azure's native service to deliver secure, compliant, and highly scalable infrastructure that meets the stringent requirement in our case. Now I am going to the next slide, which is the slide number 6, the foundation layer. So in this slide, I am going to describe about the detail what we are planning and what is the exactly I mean to say the data foundation layer we will use in the application level. So this kind of thing, let's go to the detail with the slide. So in the data foundation layer, there are different kind of activity that perform like if you see the first, I there is almost 10 to 12, but I did not able to show that, but what are the actual required and what are the most important activity that I, if you see the right hand side, I have put it in a dot and put all the different kind of activity and processes that is a integral part of the standard data foundation layer generation. Okay, so first is the multi-source simulation. Second one is, which is a different kind of connector is there where you can ingest different kind of source data. And second one is the raw data landing, preserve source field in the data lake for to prepare for the apply the algorithm. Third one is the transformation. So or not always all the data is available in a prepared format. All those data like some lob data, different kind of relational data. So different kind of data will be available. So that need to be transformed and are using business rule and data quality check. So some data need to be cleansed using different kind of data cleansing as a part of the ETL process. That kind of thing we need to do before we do optimize the data to be available for the next stage, which is the ML stage. So before that, there is some kind of optimization like performance tuning data set. Like it can, you can say like different kind of technique is there to optimize the data set. Like in our analytics, you can different kind of rank aggregation kind of thing you can do, and uh, different kind of execution layer that you can change to do an optimized tree. So in the optimization layer, basically from different kind of data sources are connected in the data lake, and from the data lake, the data is transformed, and from there, the optimization in optimized person, they build some optimized data tree. So where the data can be accessed in the most um, nearly path. So how that optimization is done is a cost-based optimization, or there is another performance optimization. These are the two way I worked with that. Optimization has been done. There is another activity which is schema evaluation. The data lake ensures backward compatibility. So my objective is in this slide is to show you all the detail or the small steps that are prepared as a part of the traditional data layer foundation. Now I am going to the next slide, which is the slide number 7. Slide number 7 is the data quality and governance enhancement. So there are different kind of, as I told, different kind of optimization is there. So like cost-based optimization, rule-based optimization, and after that, actually, there is different kind of kind of it. You can say it's kind of data quality and government enhancement as a summary. So there is different kind of processes. Okay, So first, there are almost 7 or 8 processes I have provided in that particular slide. First one is the rule-based validation. So different kind of configuration business rule is there. That business rule need to be configured, and based on that, it will validate the data and enhance data. So that business rule vary for different kind of organization and different kind of particular enterprise. So for supply chain, we will provide some kind of validation when it transfer from one geographical domain to another geographical domain, for an example. The second one is the ML-driven anatomy detection. Machine learning model continuously monitor the data. That is, and so here we will apply the ML-driven and detection. So if there is something kind of, we detect some kind of unexpected pattern, so an unexpected outliner. So as a part of using the ML, we will detect that and we will declare it as a outliner, and we will remove that on the data lake, so that we have as a synchronized and data that follow the pattern. So that way, this is a kind of a data cleansing kind of a thing. Data quality is a content. Then the third one is the continuous quality code. Then this, if you see this, these are the continuous processes that used to prepare the data for the next stage. The third one, fourth one is the lineage and audit trail. This is very much useful for the historical data. So sometime in your organization, in a particular from the management perspective, business users want to see that data. So that way, we some snapshot kind of data we required. So this is useful for preparing the lineage for the snapshot kind of data. The third one is the metadata driven automation. In the metadata driven automation, so we have some multiple type of automation metadata responsible for dry parameterized ingestion and pipeline, reducing annual configuration, enabling rapid onboarding of new data sources while maintaining government standards. So this is are the different kind of different steps which I provided in that particular slide. So let me proceed to the next slide, which is slide number 8. Slide number 8 is the intelligence layer overview. So is intelligence layer overview is in the slide number 8, which is basically the production email at scale. You can say as a summary. So different kind of, if you see the intelligence layer transform curated data. So those the data we have prepared. Now it's the time of processing the data with the GPU level and compute clusters and provide different kind of slot to those data and apply those different kind of algorithm. And if you see model, I mentioned already this part, model interpretability tool including SHAP and Lime ensures transparency and bias detection. So this kind of biasing, all kind of thing we will detect and we will apply. After that, we will the platform which supports which custom algorithm we specified for the supply chain use case, we will apply that by the rapid prototyping and deep learning complex pattern recognition. These are the summary for the day. If you see, there are automated ML pipelines, distributed compute and model interceptability. These are the different process which is associated with the intelligence layer section. Now I'm moving to the next slide, which is the slide number 9, which is the LSTM demand forecasting. In the LSTM demand forecasting, if you see, what is LSTM demand forecasting? It's a long-term long short-term memory neural network Excel. So this is you applied for some cases which I saw in the supply chain management. So some places there is different kind of complex scenario where you cannot do the normal applying the algorithm to train the data and then create the forecasted data. So this kind of LSTM demand forecasting used in those cases, complex cases. So what happened? So in the first step, it's multivariate signal integration is do, and then after doing that, the model generates the scenario-based forecasting. For example, sales or planning. It may be for finance and logistics also, and supply chain logistics also. So after doing that operational planning, scenario-based forecasting, then it pass data to the quality forecasting for different kind of scenarios. So Azure ML pipeline accelerate experimental, allowing data scientists to test the data. So in this case, what we will using these pipelines, we will accelerate the model process, which is scenario-based forecasting for our uh, sales operation planning as well as supply chain management, warehouse management process to promote the process and to accelerate the process. Okay, and this is used for the complex scenario. Now I am moving to the slide number 10. Slide number 10 is the assemble regression model. So there are different kind of model which we can use. So if you, for an example, I am doing, it was not expected that you always apply the same algorithm and same kind of thing for each scenario. So based on the different scenario and business condition, you have to apply for different cases. Suppose linear model. So where we use linear regression? Linear regression use suppose the data. If you see the data pattern, and if we identify that the data pattern not frequently changed, like after 6-7 months, it's frequently changed. So that kind of thing, like for an example, I am telling, we will use linear model, linear regression to train the data. Like different, similarly, when there is much amount of accurate result is required and use neural network, but this is based on the condition. We will apply different kind of regression model. XBoost is there, meta linear is there. This is each chapter is a different chapter where like deep architecture learn complex. So there is some complex scenario where linear regression doesn't came in picture and it will not result to a accurate result. So there neural network is used to learn some complex non-linear. So suppose there is no relationship, correlation factor is not linear, and there is different kind of curve inside the learning process and the other process. That way, in that section, we'll use some neural network, provide some hidden layer to linear, non-linear, which is interact with each other and generate the accurate result. There we will use neural network. So that is all about the different kind of regression model. There is others also. This is there is tree-based model. There is value optimizer. So I provide only 4 for a basic understanding what exactly different kind of model it is. Now I am moving to the next slide. The next slide is the reinforcement learning for autonomous decision. So this is a kind of reinforcement learning. So before we go to the reinforcement learning, we have to understand what is learning in terms of AI and ML in the Azure perspective as well as other perspectives. So AI reinforcement learning is like kind of when you have some training the model. So sometime in the first iteration or second iteration, your model have some kind of delinquency or kind of error. I mean, it is some deviation that not matched to the actual result, the expected result with the test result. So to avoid the deviation, so all the correlation, all the difference are againly pushed to the beginning of the model to reinforce the data model to calculate the difference again. That is how some that loop is provided, and we do some reinforcement learning. So using this learning, continuous learning and adaptation, we are very much reduce those difference between the forecasted data and the actual data. So this plays a major role while you examine to avoid the data accurate data difference and to get the accuracy of the data. So in supply chain management, whatever we did, so like if you say 90% or 96% accuracy is required, so reinforcement learning is play a major role for the data accuracy and data part. For that, there is different kind of uh, uh, process it involved like simulation training, dynamic routing, continuous improvement, and multi-agent negotiations. So these are all the things you can get it using reinforcement learning, and these are all the processes. Now I'm going to the next slide, which is slide number 12. There is orchestration layer. As I told, orchestration layer is all about the deployment process and the DevOps, and it's involved GitHub Action and Azure development ops to automated model registration, testing, deployment, enforcing quality gates. These are the 4 things that are involved in that particular layer. What are the 4 A? Testing, deployment, quality management, approval workflow, registration process. So So all these processes are involved in different tools and different processes, like automated CI/CD deployment is used for version control, automated testing deployment, and canary deployments. These are the another one which is used for the full deployment, drift monitoring, tracking performance, event enrichment, which is the real-time pipeline augment operational event with prediction. And fifth one is the scalable uh, endpoint. This is the auto scaling interface infrastructure support. So these are the different kind of deployment and testing and enforcing quality that we require for the orchestration layer. Now I am moving to the next slide, slide number 13, which is the government security and compliance. So this is all about model transparency, AI fairness, assurance, zero trust, security, and unified governance. These are the four kind of uh, mm, activity more sub processes that divided into the different kind of steps and processes like a SHAP, shapely adaptive explaining, Lime local interpreted model apology explanation. So these kind of mm, processes involved in all the security compliance and other process and other processes. So governance of the data. So this is all the say I have mentioned in this slide. So I'm moving to the next slide, which is slide number, which is case study, proven business impact. Okay. So for an, if you see two kind of thing we did, automating manufacturer and global logistic provider. Excuse me. So for this one, if you see the Tier 1 automatic manufacturer deployed the Azure-based architecture across the North America, which predicted the demand. If you see all the detail, so how accuracy we mean does forecast accuracy 89%. We have used LSTM model optimization. Okay, and then inventory reduction we applied, so it's get 12% optimized 12%, and time scalability optimized 18%. This kind of different kind of service level 97% maintain excellent with cutting cost. As I told, cost rate optimization we did. This is for the automotive automotive manufacturer, which is based on the not, I mean, this is a different kind of use cases. Another use case is like a global logistics provider we provide, if you see. So there is some fleet chain efficiency is provided after that. Okay. That we have implemented predictive disruption monitoring. So that the 7 to 14, 2.3, 41. These are the all the things actually can be achieved. These are the different kind of case studies. Now I'm moving to the next slides. Next slide is future detection and conclusion. Future detection and conclusion. It's kind of the what the capability. We have not used all the capability. There are other capability inside the AI Azure cloud infrastructure that maybe uses a to implement multiple scenarios and multiple optimization in the supply chain, and you can build multiple application using this platform. So among these, I provided some of that, but there is others also. There is lots of capability in AI and Azure cloud, so you can use and you can implement and you can implement in different sections. The first of one is like a federal learning. Second one is the generative AI cockpit. Third one is the multi-agent RL system. Second one is the self-hacking, self-healing network. So these are all the system. So in the self-healing network, supply chain automating the supply chain that autonomous detect and direct the HBL, house bill of landing, then the shipment, then uh, the inventory process where it is in the warehouse 1 or warehouse 2, then the human actions which triggers to move shipment from one kitchen to another warehouse. This kind of thing, this kind of automation. This is a the top of the iceberg. There is lots of things which we can do using AI and Azure cloud interface. So some of thing I have showed in that particular my presentation, but there is others also. So this is all about my presentation, and thank you to all of you. Thank you a lot.
Very good, Purav. Very interesting stuff there with the AI stuff, especially. I've been doing a bit of stuff with agents and multi-agents, and I see you had that in there as well. Um, we don't have any questions in on the comments yet, anyway. So if there's anyone, Ishan or Dan, do you have any questions?
Not at this time. That was great, though. Great overview.
Yeah, very good.
Thank you so much. Thank you. Thank you.
So,
Thank you.
Ishan, I'm going to share your screen there now, and I'll let you start. There you go. I can see it there now.
Right. Yep. Thank you, Frank. Hey, good day, everyone. Thank you for being here. I'm Ishan, and a little bit about myself. I'm a senior software engineer working at NVIDIA, and I'm an alumni of the Carnegie Mellon University. I have a 10 plus years of industry experience, and today I want to talk about something I'm really excited about. I'll get started. So today, the world is changing fast in this age of AI and deep learning, and that's fundamentally changing how we think about manufacturing. For decades, we have viewed automation as a choice. You know, either you have humans doing the work or you have machines. But what if there was a third option? And the third option is that, hey, like both humans and machines could work together as true partners, each bringing their unique strengths to the table. Well, it does sound like sci-fi, but we're gonna explore how we may be able to achieve that. So we will look at how cutting-edge AI and robotics are helping create partnerships, and that can make workers more productive, safer, and even more engaged. So this isn't about replacing people; it's about elevating them. So let's dive in. Next slide. Yeah. So, what does this new paradigm actually look like? Like for the past 50 years, automation has meant just one thing: remove the human from the equation. Like we program a robot to do a task and it does that task the same way every single time, very reliably. But here's the problem: manufacturing, we know, isn't static. Conditions keep on changing, products keep on changing. We have the iPhone 15, 16, 17 Pro. Everything keeps on changing, and workers need change too. And when they do, the rigid automation definitely breaks down. So we have like hundreds and thousands of engineers working round the clock, just updating these paradigms and programming on these existing rigid systems every day in, day out. But what we are talking about today is different. It's really an augmentation and not a replacement. So we need to imagine an AI vision system, for example, which is working alongside a human inspector. Like, the AI flags potential defects in real time, but the human makes the final call. So the human brings judgment, context, expertise, a lot of experience, and AI brings in speed and consistency. So together they are better than either could be alone. That's the theme and that's the vision. And this is, we can term this as, like collaborative intelligence. So, and well, whether we believe it or not, it's happening right now. So, yeah, moving on to the next slide. So, let's talk about the technology that makes this possible, right? So, we need real time collaboration. Real time collaboration requires processing at the edge. That means on the robot itself, not in the cloud. Why, do you ask? Well, because milliseconds matter in the real time systems. If a Imagine if a robot has to send the data that it is capturing to the cloud, wait for a response, and then act. We are looking at latencies probably in the order of seconds. Well, and that is not natural, or that's not what like we think the real time like application would be. We need a system that can process the data locally within a sub 50 millisecond response. And by 50 millisecond, like a lot of research have shown, hey, like 50 millisecond around, that's when things feel natural, that's where our brain thinks it's like a continuous motion and not a like a stepwise function. So yeah, that's fast enough for a human and robot to like work together seamlessly. Second, we need very high accuracy. The neural networks that needs to be trained on like thousands of hours of factory footage across different lighting conditions, angles, different worker demographics. That diversity in training data is what it will get us to the high accuracy number. And third, we need resilience. Well, imagine this, right? Like if your internet goes down, the system needs to keep working. This is critical for manufacturing environments specifically, where uptime is everything. We cannot afford an internet outage which brings the whole factory to a screeching halt. Think about it, right? Like how much just does one time of downtime actually cost a factory which is like a big like a big like facility. It's easily tens of thousands of hours. So we need to think of this as an edge AI architecture, and that edge AI architecture eliminates that risk. So next slide. But well, multimodal sensing, right? But processing speed and accuracy just aren't enough. These robots need to truly understand what's happening on the factory floor. That's where the multimodal sensing comes in. Just like humans use all of our five senses to understand the environment, the robots need to use multiple data streams. They need to use cameras for visual recognition. They probably would use things like force sensors for detecting pressure, resistance of things they are like interacting with. They would use audio sensors. Audio sensors is more like like your microphones to probably detect some kind of anomalies. For example, like some unusual sound is coming from like a part of the assembly line, and that can detect some that can probably tell us, hey, it may be some like equipment causing some problems before they become really critical. So we kind of like we also consider the uses of depth sensing and even inertial measurements, which allows the robot to know its own state in the 3D world and also understand the environment better. So why does this matter? Well, because a single camera might misidentify an object, but when you combine information from the multiple modalities, the system has a high confidence. This prevents false positives, which would disrupt the factory workflow while we catch the real issues. So, this multimodal approach is inspired by how humans work naturally and assess situations. We see this deployed everywhere today, especially in the autonomous vehicles. Both Teslas and Waymos have this, they have more than one sensor working for them. And they don't rely on a single sense, right? Like they integrate information from all these multiple modalities to make the final decision. So, next slide. So now let's talk about what a natural collaboration actually looks like in practice. Well, the system learns individual worker preferences and it needs to adapt its communication style to the worker. Like some workers, like maybe me, like we prefer visual cues. Like lights, displays, screens. Some would prefer audio feedback. I think it will also depend on what kind of factory floor they might be working on. Some would prefer haptic feedback like vibrations, and they may want to communicate intent without words or even without screens at all. So the system needs to be fluid enough to figure out what works best for each person and adjust accordingly. And there should not be like any need of a special equipment. Like there are no complex interfaces to learn. The robot needs to adapt to the human and not the other way around. Right now, for the last 50 years, we have developed machines where humans need to develop the skill set to work and adapt to the machine, to work, to know it better. This is a paradigm shift. So this allows AI enhanced robots to help with let's say, quality inspections by highlighting potential defects, and may even learn from, over time from the experts who are on the factory line, which is humans. So these systems help with assembly assistance by adapting to worker style and techniques and provide support. These systems also help in proactively identifying potential issues, which will help with the predictive maintenance and prevent any downtime on the factory. So, yes. So here where it gets really interesting. I mean, like, we all know that the traditional manufacturing assigns fixed tasks. Like, for example, worker A does assembly, and work, and a robot B probably does welding. So every single day, the same task over and over again. But what happens when the worker gets tired? What happens if a machine breaks down? These are important questions. This is like, when I'm working, I need a break after doing the same mundane task, for more than maybe 2 to 3 hours, right? So the system becomes rigid and brittle. A multi so a s- Probably a probable solution there is a multi-agent reinforcement learning system, which can solve this problem. So it continuously monitors worker fatigue, robot efficiency, and even the task complexity, and then it dynamically reassigns the work in real time. For example, if a worker has been doing repetitive assembly for 2 hours, the system might shift them to quality inspection, work that requires human judgment, while the robot takes over the repetitive tasks. This isn't just about productivity, it's about worker well being, it's about preventing burnout. The system learns from the outcomes that it sees. If a particular task allocation leads to higher quality or even faster completion, it reinforces that pattern. I think, yeah, that's very obvious here. And the system gets smarter every single day. So, yeah, moving on. So, but among all this, where does safety stand? So, safety in on factory floor is non-negotiable. So yeah, let's be very clear about this, how we approach it. The system needs to have multiple layers of protection. Here in this slide, we are talking about three different safety mechanisms that can be built in. For example, the first one that we talk about is the LiDAR safety zones. These zones create dynamic parameters that adapt to worker proximity. When a human enters a defined zone, the robots either slows or stops. I think that's what we naturally expect to be in a world which is going to be more predominantly filled with robots. And then when the space is clear, then they probably work on full speed because there's no human, so no human will get hurt in that area. Second is like a force torque sensing. What this is like a fancy way of saying, okay, it has some good sensors that kind of tell if something is interacting with these robotic arms or these robotic movements. So, or these robotic joints in general. So these force torque sensors, which are embedded, they detect unexpected contact within pretty like a few milliseconds, and then they trigger immediate protective stops. And third, we also use like real-time path planning that continuously recalculate robotic trajectories to avoid collisions and even predict human movement patterns. So an example here could be that, hey, like you're inside Costco and, like there are robots. Imagine a Costco with robots, which is moving stuff around. So, but there are a lot of people in one of the aisles and a robot was going there. So now a robot can see, okay, there are too many people. Maybe there are certain things that are blocking the path. So it will try to use like dynamic, continuous, real-time path planning and try to take another aisle to reach its destination. So talking about safety again, right? So can a robot hurt someone? Yes, it can, and any machine can. But this system is designed to take is designed with multiple safeguards to make incidents extremely unlikely. So safety doesn't have to be an afterthought here. It needs to be a core design principle when we're designing these systems. So what does this actually mean for the bottom line? So let's walk through some of these numbers, right? So The 23% quality defect reduction comes from these AI vision systems that catch inconsistencies that human may miss due to fatigue or attention lapses. The 15% cycle time improvement via the idle time optimization, and even a 67% reduction in the assembly mistakes during complex procedures lead to significant productivity gains. The safety improvement reflects fewer incidents due to predictive hazard detection. So maybe we can try, make these numbers a little more tangible. So, for example, a facility producing, let's say, 10,000 units per month, and they have a quality defect rate of 10%. So that's like 1,000 units per month have some defects. A 23% defect reduction means 230 fewer defective units. And maybe let's say that, there was a cost associated to rework a defective unit to make it perfect again. Let's say that's $50 per unit in rework costs. So that easily amounts to just around $12,000 in savings per month, just with these fewer defective units. Scale it up to the whole year, that's almost $140,000. And once we start taking into account the additional savings that we get from the cycle time improvement and the onboarding time savings and the error reductions, this can easily scale up to by an order of magnitude, even into millions. So this is the most important moment here. I think we need to ask ourselves that what would these improvements mean for everyone's bottom line, who are especially working, who are like owners of different factories and maybe different production lines. How does this translate to their savings? Moving on to the next slide. So here, and this is another important moment. Like we talked about safety, we talked about the bottom line, but if it's collaborative, we need to make sure that we are kind of earning the trust of the worker at the end, right? So this is something very critical for the adoption. Workers need to understand why the system made a certain decision. In fact, we see around us right now that a lot of things, like computers have replaced humans in a lot of places. You go to a store, you talk to someone, someone is helping you check out, and they say the system's not working. So system in the background has become their boss, let's say that. And a lot of times we don't know why a system is making a decision, why is showing up a certain error or is showing a certain decision. So in this system, which is even more abstract, we cannot just accept it blindly. We need to understand why a system made a decision, and the system needs to provide a certain level of transparency. When it recommends a task reassignment, it needs to show the reasoning. For example, like it says worker fatigue detected after 3 hours of repetitive work. So now it will switch the worker to the inspection task. Now this isn't a black box anymore. This kind of explainability builds trust over time. A worker who understands the system's logic is more likely to accept its recommendation and even work collaboratively. By incorporating worker feedback into the system design from day one, we can make sure that the system learns from their input as well. Now, I know what some of you might be thinking, that will this system like spy on the worker? Well, the short answer is no, it won't. System task like the system tracks task completion time and quality metrics, and not really the personal conversations or any of the bathroom breaks that they may take. The goal is to support workers and not surveil them at all. Moving on. So what kind of human factors would go while designing this kind of product? We need to design this for the people, right? So the human factors critical for this design, 4 pillars have been identified here. So definitely we need to do extensive user testing with actual factory workers for the industry that is in question here. Right, every industry will need different kind of will have different kind of user testing, will have different type of inputs from the uh, factory workers here. We need to do ergonomic studies to ensure that the system actually reduces strain rather than increases it. Workers' cognition load needs to be assessed to make sure that workers aren't overwhelmed by the information that the system is producing. So I'll walk you through some of the interesting findings, right? So, for example, it was discovered that some workers preferred visual feedback over audio in noisy environments. I guess that makes sense. So we also need to adjust our interfaces accordingly. The system needs to work for workers with different abilities, ages, and experience levels. So we really are looking for a kind of system that fits a different set of people here, right? So we need to make sure that the training of workers with these system is also now taking just a few hours instead of initial weeks of onboarding. We need to test these diverse demographics with to ensure that the system doesn't have any kind of hidden biases. So these are the problem statements that we need to work around while designing these systems. This is how the continuous feedback loop can be set up and update the system with the feedback and newer findings. And all of these factors will govern the trust the workers will develop for these new edge AI based systems. Moving on to the next slide. Uh, Predictive maintenance. So let's shift gears and talk about maintenance, right? So unplanned equipment downtime is one of the manufacturing's most costly challenges. We want to reduce it as much as possible. These systems combine, like a lot of sensors today. Everything is IoT. We have IoT sensors, temperature, vibration, acoustic data. We have machine learning in place now to predict equipment failures before they happen. That was the whole selling point of IoT in the 2010s. But here's the key part here, right? This system doesn't really replace the maintenance technician. It alerts them with very high confidence predictions. For example, it may flag, hey, the bearing X on machine Y will probably fail in next 48 hours. The technician then uses their expertise to decide, well, do we replace it now or can we get it like another shift out of it for another 24 hours before we replace it? So this is the augmentation in action. The business impact that it will make is also pretty significant. We know that a single hour of downtime is in a high volume facility can cost tens of thousands of dollars. And this kind of predictive maintenance shifts you from reactive fixing to proactive, where we prevent the failures. System learns from the maintenance history. Each repair feeds back into the model, making predictions more accurate over time. I guess the term that we might be looking here is the data flywheel that is used in different uh, industries. So it's kind of a data flywheel where, continuously it's a continual learning model. Everything, every fix, every new input makes the system better over time. And this is a virtuous cycle. Like better predictions lead to fewer surprises. Moving on to the next slide. Uh, so now the practical question: how do we actually do this? Every decision maker, needs to be asking this. So here's like implementation framework. First, we need to make sure that we are ready, right? So we do an assessment for the readiness. We first evaluate any current infrastructure, identify gaps, and determine what upgrades are really needed. Second, we need to do a pilot deployment. We start really small, we learn, we iterate. Here, every system, every industry will have different needs, and we may need to iterate accordingly. This also reduces risk, and it builds kind of internal champions. Some people will really like it, and in the organization who will become the advocates of this kind of system. I guess a lot of this, like a real example of what this may be looking like is, like the adoption of AI assisted tools in a lot of companies for coding. Like we are using Cursor now instead of just VS Code. So this is something like, like a few people use it, they really like it, and they're like, hey, we should definitely use this. There's no going back now. So Third would be like a timeline and a change, and change management. For example, typically it probably like 3 to 12 months from decision to full deployment of this small to full scale deployment. And it can depend on the facility complexity, the how long would it take for the technology to roll out. It's also a cultural shift. We will need training programs, we will need clear communication to all the workers that why this is happening, and we need to have mechanisms for their feedback too. So moving on to the next slide. So, well, now let's address a specific pain point that traditional automation cannot solve, which is high mix, low volume production. So the problem statement here is as follows. The traditional robots are programmed for specific repetitive tasks. For example, if we need to produce 100 units of a certain type of spring, and then 50 units of certain type of switches, and 200 units of certain type of, I don't know, like a box. So the changeover time and reprogramming costs to make these robots economically and viable. Like now if I need to make change, I need to make 5 different type of springs, I need to program those machines every time differently. So but uh, this kind of system solves this through flexibility. We all know that AI is a very flexible system. So these robots, because they use AI to enhance and understand the intent, they can adapt to the new tasks much faster. A human can now show the robot the new assembly process, and it just learns in one shot. There's no weeks of programming required. This kind of opens up automation to industries that have been even locked out of it, like aerospace, medical devices, even custom manufacturing. These are very high margin businesses, and these employ a lot of people, and they have a very high turnaround time for their new products. So this solution makes automation economically viable for them. And another benefit on top of it is resilience. So it if demand shifts, we can quickly pivot the production without any massive capital reallocation, because these systems are very flexible. So I think that translates to a huge competitive advantage for anyone who is already using this. Next slide. So, yeah, let's zoom out and let's talk about the bigger picture here, the future of manufacturing. So, the future of manufacturing, we see a lot of things. I've listed three, I will talk about two more in addition. So, first and foremost is worker empowerment. So, we need to make sure that people are not really getting replaced, but they are elevated, they are augmented. They move from these repetitive physically demanding work to a higher value activities, which is problem solving, quality assurance, and process improvement. And this is better for a lot of workers. Why? It leads to less injury, it leads to more engagement, and it also leads potentially more fulfillment. They are not bored now. And it's better for companies too. It shall lead to higher retention, more innovation, and even a better culture. And in addition to the operational resilience and the competitive advantage, we theorize environmental and economic and sustainability as well. There is environmental sustainability is achieved via use and proliferation of optimized processes, which reduce waste and and energy consumption. We already talked about in one of the slides earlier where we saw like 23% reduction and 67% reduction in the errors, right? So that automatically translates to like a wastage reduction and reduced energy consumption. We have economic sustainability, and we achieve that by making automation accessible to more manufacturers, including small and medium enterprises. This essentially democratizes the productivity gains. I would like to say that this approach is indeed future proof. And as this technology evolves, our human centered philosophy ensures that humans remain central to manufacturing, and we don't remain peripheral to that. And yeah, I think we are almost out of time, so I'll move forward quickly. So, last slide. So yeah, what are the key takeaways, right? The key takeaways are that first, yes, we need a sub 50 millisecond latency and a 97% accuracy in these edge AI systems for this to work. We need to make sure that safety is paramount, productivity tags along, and both of these go together. Third, the human element. This technology is designed with workers for workers. It's not about replacing people, and it's about amplifying their capabilities. And finally, the business outcomes. We need to have measurable improvements in quality and productivity that translate to return on investment and the bottom line impact. Yeah, thank you.
Very
Great
good.
job.
Especially, I come from a manufacturing background myself, Isham, and I was very focused on everything. I suppose companies would really kind of, be focused on the ROI, return of investment in the robots, especially like 23% there. Your example and the 67% savings is huge, so it's
Yeah,
very good.
thank you.
Yeah, we don't have any questions in the chat there, but Dan was talking about some of the data center stuff could really do with this.
Yeah,
A lot of times it's not, it's not reducing failures unless you can do that, but it's figuring out when there are enough failures to go in and, replace or deal with it. And a lot of that is, robotics could help quite a bit with that.
Yeah.
I mean, in the software industry, we already have a lot of these implemented. Like we kind of have monitors of every kind everywhere. We just
True.
keep on writing scripts every day to, like make our lives easier. So I guess that's all about translating that to the industry now.
Yeah.
Heavy industries.
Yeah. Well, and to your point, if things aren't resilient, like if the internet goes down or if, certain aspects of the manufacturing go down and are unavailable, then, downtime is costly. So
Yeah.
great presentation, great insights.
Thank you.
Very good. Dan, any news for us? Any interesting stuff coming up?
I think my news for the new year is that I'm an MCT alumni. I decided not to renew my certified trainer just because I'm not using it actively. I'm part of the alumni for now, at least.
Very good.
Yeah.
So I see StreamYard, that other provider, Bending Spoon, has taken over StreamYard.
Yeah, I got a heads up on that from my employer that they, besides, I guess, another product they use, StreamYard, or own StreamYard now too. So did they send you something about the subscription or?
There's when I opened up the program there, the header was up there.
Okay, that's interesting. I haven't seen that yet, but
yeah.
I'm logged in on my phone, so I'm getting a very, very compact view of StreamYard, if you will.
Very, very good.
Cool. Well, Happy New Year.
Yeah.
It's 2026 officially, so that means 3 years, right, Frank?
Yeah, 3 years of the Azure and AI Show now, yeah.
That's awesome. Congrats.
Very good.
Congratulations. Yeah.
So, we'll end the live stream. So, guys, thanks everyone for joining us. And if anybody wants to watch over some of the live streams, we have them on YouTube and they're on LinkedIn as well. So thank you very much. We'll be back here again next week with some new speakers. And I'm hoping to do some more stuff with those AI agents, maybe do some demos on them. I think this year is going to be the year of all the agents. And hi, Charity, how are you?
Hi, good. How about you guys? Happy New Year.
Happy New Year.
Happy New Year.
Just running around. Grandma errands.
Oh, very good. So
Yeah,
I'm just ending the live stream there anyway. So thanks everyone for joining us.
Thank you, Frank.
Bye, everybody.
Be safe.